Good morning, everyone. Thank you for being here today. I'm very excited to have the opportunity to speak on this topic today. I'll be sharing our bug hunting journey in VMware device virtualization. Okay, firstly, I'd like to introduce our team. My name is Zibo, and I specialize in IoT and virtualization security. And I had the privilege of working with Jiaqing and Zhenghao, who have been key contributors to this work. Unfortunately, they couldn't be here today due to the other commitments. However, their contributions are integral to this presentation, and I will do my best to represent our work. We are all working at the Tianfu team of Legend Cycle at Tianfu Group. Our team focuses on vulnerability discovery and exploitation. Our work have been published in HITB, Black Hat, SP, Unix, and CCS. We are also the winner of GeekPong and Tianfu Cup. If you're interested in our work, you can follow us or visit our blog website. Okay, let's start the virtualization hacking journey. Originally, our team focused on IoT security research, but we plan to expand the scope of our research. So everything started from our leader told us to pick a traditional software interested most to do research. Since we didn't have lots of experience with traditional software security, so we had to be prepared for long-term research. We have lots of target Windows, Linux, especially their kernel. Also, we have interested lots of things. We soon found that the virtualization almost involve each of them to some degree. So we finally chose virtualization as our target, even we know nothing about it at that time, and we absolutely can learn a lot through research virtualization security. Here is the history of our virtualization security research. We started to research virtualization security at the end of 2022. Virtualization technologies by studying public examples. Then we managed to escape Parallels desktop on GeekCon 2023, and we also reported many bugs to VMware. Today, we will take you to look back our VMware virtualization bug hunting journey, include two parts, VMware Hypervisor reverse engineering and device virtualization bug hunting. Firstly, we will introduce VMware virtualization architecture to you through reverse engineering of the VMware Hypervisor. This helps us to figure out which code and how they can be influenced by attacker, and hopefully it will bring a new view to you. Okay, let's go. To reverse such complex system, you can't just rely on IDE Pro. For VMware Hypervisor, we have some recommends to speed up the reverse procedure. Mainly contains three parts: debug tricks, dynamic instrument tools, and symbol recovery strategies. It's important for us to debug the VMX initialize process, so we need to attach the debugger to the VMX as start. Normally, it should be able to do that by configuring the image file execution options, but it won't be work on VMX. So we add the breakpoint at the entry point of the VMX binary. Next, we should enable the WinDebug post-mortem debugging option. Now, once we start the guest machine, the VMX will be crashed due to the breakpoint, and the WinDebug will auto-attach to it. Dynamic binary instrumentation can also be useful when reverse the VMX binary. You can use Breda to test the function arguments or use it to hook device emulation code and see its execution flow. Something can be traced like graph commands and USB commands. Although VMX binary didn't have symbol information, but open VMware tools shares a lot of code with VMX, especially some general structures and functions like hash tables, events, and async socket. Of course, we can learn a lot from the old CVEs, hardware documents, and even open source code like QEMU Linux driver. All this can help speed up the reverse engineering. We have prepared well for this for the reverse engineering, but where exactly should we start? If you already learned something about Hypervisor, there is always a loop that handles switch in and out of virtual machine. So we will locate the loop code and start the reverse work. We know that VMX is a user mode process. It should access kernel with for switch in. So there should have a kernel mode module. In Windows VMware Workstation, the kernel module is VMX 86.6. And in ESXi, the VMX just directly communicated with VMKernel. So we need to pay attention to the interaction between kernel and VMX. To understand those IO control code, we can combine it with log string and VMX binary. For example, the code in picture should represent the IO control VMX86 run VM, which may be the call to switch in guest machine. By looking for references of this function, we can easily locate the main loop code. You can see that VMX uses IO control run VM, switch into virtual machine, and blocked until virtual machine exit to host. VMX will get the return code and call the corresponding user RPC handler to handle the virtual machine request. What is the user RPC? It is a mechanism that VMware designed for VMM to interact with VMX on host. It is very similar to hypercall, but it is in user space. User RPC handler will only take one argument, which is user RPC block pointer. User RPC block is a shared area memory region, which is another mechanism for shared data between VMX and VMM. So we want to know what it is passed in user RPC block. We should figure out how the shared area works. The implementation of shared area is related to the creation and loading of VMM, so we need to start it from the initialize process and pay more attention to every memory allocation cost, and also remember to check the interaction between VMX and VMX86 kernel module. Follow the initial process, we will notice that there is a ELF object called VMM blob embedded in VMX. There are several VMM extensions stored in VMM modes section of VMM blob. There are also ELF object. Good news is VMM blob contains lots of symbols, and these symbols shared with VMX and VMX86 kernel module. So this can also speed up our work. By analyzing these codes, we can find that VMX will link the extensions with VMM blob in memory to construct the actual VMM process according to the user's configuration. Also, we found that there are predefined export symbols such as the user RPC block, and the corresponding mapping arise in the another section. This is because some virtual devices require shared memory will need link to it too. After these symbols has been defined, VMX will calculate the total size of shared memory and allocate the memory space. Now we have figured out how shared memory was allocated, but how do VMM access them? We found that VMM blob has another two specific sections. The one contains the GTT information, and the other one contains the virtual address mapping information. Combine this information, VMX allocates the memory and building page table structures based on VMM blobs information. VMX86 kernel module gonna further populates the page table information and load the VMM file, which is constructed by VMX. VMM blob, VMX86 .sys work together to build the VMM running environment. When everything prepared, VMM should be able to directly access the memory allocated by SharedArea module. Now we have figured out how SharedArea module works. We still need to figure out how VMM switch works to understand the user RPC. Cross-page played an important role in VMM switch. It's one page size memory region used for storing context between VMM and the host, just like VMCS in interVT. When VMX call L control run VM, VMX86 kernel module will save the current CPU state to cross page and restore the VMM CPU state. And the operation of switch out is on the contrary. We found that user RPC is implemented through a platform user call in VMM. It saves the user RPC opcode and the platform call invocation number in the cross page. When platform call 100 is executed, VMX86 kernel module will return the user RPC opcode to VMX, and then VMX could call the corresponding user RPC call handler. Whenever VMM prepared to call user RPC, you will see VMM modify the user RPC block to transfer data to VMX. These are basically the implementation about user RPC. It is the basis for almost every emulation implementation. Based on the knowledge, we are able to further reverse engineering device virtualization. Since we need to analyze data flow between guest to hypervisor, we need to figure out the I/O emulation. For port I/O, VMM will resolve the I/O instruction and attempt to use the user RPC to call VMX to finish the process. In VMX, port I/O callbacks have been registered as the code in the page user RPC 317 mentioned in the last page will call the port I/O callback. Note that not all the port I/O callback registered in VMX. There are also some devices implement their I/O callback in VMM. For MML, in most cases, VMX associates the memory region with a specific ID and the callback function defined in VMM. They may access shared area to transfer data to VMX, so we need to read the code in VMM to figure out what happened when access the MML region in guest machine. Most MML operations in VMM will call user RPC to handle device emulation. This is why we said user RPC handle lots of device emulations. Physics memory access is another important I/O operator we need to analyze. We will not discuss too much about the memory mapping structure, but we should mention that on Windows, the main guest memory is mapped as file, differently on ESXi mapped by VMKernel. When VMX gets the physical memory region object, it will check the type first and directly access the pointer field mostly. Overall, this graph describes the results of our VMware Hypervisor analysis. It is worth mentioning that there were some differences in SCSI. We found that some virtual devices MML will not always call user RPC, only if the hosted emulation option is true. Instead of using user RPC to interact with VMX, they use VMK call to direct call VMKernel to handle device emulation. So, although VMX are identical on ESXi and Workstation, but the virtual device emulation code won't always be the same by default. Through the reverse engineering of VMM, we not only figured out lots of structures in VMX, but also confirmed that the scope of our research for vulnerabilities. And in particular, we found a new hypervisor model could be attacked, which is named the VMKernel. These three are the main binary modules we need to consider when hunting bugs in VMware virtualization. Bugs in them possibly influence the host. Let's enter in the second part. VMware device virtualization bug hunting. Generally, there are two types of strategies of vulnerability discovering. We try to do the automated analysis by buzzing the target device and manual analysis by reverse the device implementation. For fuzzing, we tried two solutions. Firstly, we try to find some functions suitable for fuzzing. We're using Farida to call the target function and use Stalker to get the coverage information. However, the DBI is very slow and the function may be influenced by other threats or global variable. Even worse is that the test case poke may not work because there may be other checks in real execution flow. The second solution, we tried to input the test cases from the guest OS to virtual devices directly to accelerate the transmission of test cases. And we can hook a function from guest OS inside to get the corpse and use binary instrumentation to collect coverage information. There are also some drawbacks like coverage information may not be accurate because the guest OS itself may also trigger the code, and this requires to figure out how to access the device so that we need to read lots of device specification or driver's code. Although we put lots of efforts to fuzzing, but we didn't get good results. If we want to improve the mutation strategies, we need the right code that meets the specifications of the different devices. We don't have much patience to improve our fuzzer. And since we have already read lots of device specifications, and so we finally decided bug hunting manually. Next, I will talk about the bugs that we found in USB and the SCSI virtualization to introduce the possible source of a threat in virtual devices. Basically, we can divide the USB emulation into three parts. USB host controller emulation, VUSB emulation, VUSB backend device emulation. When guests want to access the USB device, it will write data into memory and access the host controller MML space, which will trigger the VMM handles the MML access, calling the corresponding user RPC call handler in VMX. Then it will convert the data into a URB object and eventually proceed by backend USB device. And if it tries to access the USB device, plugging in host machine finally, there will need another service to help. The first bug in the host controller part, and it is an uninitialized memory bug. In the transmission control protocol, USB devices accept multi types of requests, one of which is standard device request. The request packet begins in the format of setup packet. So it will contain 8 bytes at least, and it has a field named W-length. Indicates that the length of subsequent data. The standard device request serves as the payload for USB device. However, the host controller do not transfer data based on this unit. For example, in HCI, data is transferred in units of transfer descriptors. When VMX handles the UHCI emulation, it retrieves the first TD on Q head, extracts the W-length field from setup packet, and use the size to determine the size of data buffer for URB object. After allocation finished, it will copy the data into URB object, and they do lots of check to prevent buffer overflow. Look back to the process, we found that different types of backend USB devices will result in URB objects with varying private structures, and the URB object could be controlled. For example, HITB device will allocating URB object without additional fields besides the data buffer of the URB. Also, HID device will use malloc for data allocation. There are some problems here. Allocating W-length size URB does not mean you will get W-length size data from guest supplied TDs. Malloc allocation left memory uninitialized. So, backend USB device will return data use the same URB buffer, so it will eventually leading the heap data leaked to the guest. The second bug is user after free appeared in the USB emulation code. The SCSI, there is a structure called the device context, which stores the USB device status. It is constructed by device slot context and endpoint context. Device slot context holds USB device information. Endpoint context holds information for a single point. Also, each endpoint has one or more transfer rings. There are transfer request blocks on the transfer rings, and the SCSI transfer data based on these structures. In order to explain this bug, we need to look back an old bug in 2021. It only alters the sequence between the calls to release transfer ring and the code that assign values to endpoint context. Let's first figure out how transfer ring release works. First, it will get transfer ring object from the endpoint context. Then it will retrieve the VUSB device object based on the USB port number saved in the device slot context, and then it will obtain the VUSB pipe object from the VUSB device object based on endpoint ID. After that, it will release all the URB objects on the VUSB pipe object. Finally, the transfer ring object will be released. Also, it will release the possible URB objects on backend USB device in case there may be dangling pointer on backend USB device. It seems no problem here. But however, it actually not the URB object could become dangling pointer. It is because that the transferring object pointer is not only held by endpoint context. URB object also holds the pointer that points to a field of transferring objects, and this field is responsible for tracking the corresponding transferring object when ESXi returns the USB device response to a guest. Before the patch, ESXi command like configure endpoint could modify the endpoint context contents before releasing the transfer ring, so it may be lead to the tab stored in endpoint context mismatch the VUSB pipe object tab. This will cause the function return without a VUSB pipe object. Let left URB object on the VUSB pipe object not be freed, and the previous pointer now becomes dangling pointer and causing user use up free. For our question is after the patch, is it possible to make the VUSB pipe object mismatch again? We know VMX will need to check the port number stored in slot context to find the VUSB device object. If we can modify the port number, it may cause VMX find a wrong VUSB device object. So if in that case, it will also find a wrong VUSB pipe object. We do have address device command can make this possible. You can see the address device command only modify the slot context and control endpoint context. So first we finish the device configuration process and we create a transfer ring on non-control endpoint. Then we transfer URB data on those transfer rings. In the end, we use the REST device command on that device to modify the device port number. Now, if we try to release transfer ring on that endpoint, it will fail to find the right VUSB pipe object and cause UAF again. The third bug is in the USB backend device emulation, and it is auto-bound read vulnerability that will be triggered within the system API. The guest OS communication with smart card through the virtual smart card reader. Guest OS use CCID protocol to communicate with virtual smart card reader. The APDU serves as the payload for interaction between the smart card reader and the smart card. Their relationship is similar to the host controller and the USB device. You may already see that both data structure has a length field. Such length field always needs to be carefully handled. VMware do checks whether the message learn field of CCID protocol matches the learn field of command APDU. But it fails to verify whether these two fields conform to the size of URB buffer. It directly uses these fields as arguments to call the Windows S-card transmit API. Clearly, S-card transmit cannot check whether the length matches the data buffer. So it will auto-bound access the heap data and write it to smart card on your host. Also, we may be able to read it back. So it's kind of interesting. In conclusion, host controller emulation, VUSB emulation, and USB device emulation all could be attacked. And we still have more cases. Besides maybe more attack scenarios in the future. For example, maybe plug in evil USB device and leverage VMX to execute the code, or leverage your local USB device to privilege escalation. It's very challenging to defend such a complex system. Okay, next, let's start the SCSI part. As mentioned earlier, ESXi has a new attack surface that is different from Workstation, VMKernel. This is difference very obviously in the SCSI code. Next, I will show you the difference in SCSI in detail. This is an overview of the SCSI data flow. You can see that there are two paths for writing data to the disk, one through VMKernel and one through VMX. These are two completely different code paths belonging to ESXi and Workstation respectively. The specific code path of SCSI in Workstation is shown in the finger. If the user calls the SCSI IO request command, it will enter the process SCSI IO message function, where it will confirm whether their environment is hosted emulation. Finally, the hosted process SCSI IO message function calls the relevant handler in VMX through user RPC. The specific code part of SCSI in ESXi is shown in the finger. ESXi divides the situation into whether the environment itself is in hosted emulation, and if it is hosted emulation, it will be the same as the Workstation path. Otherwise, it goes to VMK process SCSI IO message. Go to VMKernel through VMK call X. Because of this small code gap, ESXi has a new attack service that Workstation does not have. Next, I will introduce the vulnerabilities we found on those two different paths. The first vulnerability we will talk about is located in VMX, and the official description is out-of-bound read and write vulnerability. As a tool for storing data, stability is the most critical and basic requirement for disks. VMware implements corresponding disk verification capability in device emulation. One of the disk verification capabilities is to detect data corruption through checksum. This is where the vulnerability occurs. Before we start, let's introduce the SCSI command. In the SCSI command's reference manual, there is a command called write that allows to operation of 8-byte logic block address and 4-byte transport length. This shows that we can use this command to access any address in all 64-bit space, provided there is no disk capacity limit check. VMware did not implement the disk capacity limit check in its disk verification program implementation. As can be seen in the figure, after applying for a heap of corresponding size according to the disk capacity, only the operation is checked to see if it is read or write operation. Obviously, this is a heap overflow. The write and other read and write commands in the SCSI command reference manual allow us to access any 8-byte address. This allows us to easily perform arbitrary read and write operations. The vulnerability we will discuss next is located in VMKernel, and the official description is out-of-bound read. Still start with the SCSI commands reference manual. There is a command called Unmap, which can unmap one or more logic block addresses. This structure of Unmap itself is relatively complex. and is divided into 3 parts: unmap command, unmap parameter list, and unmap block descriptors. Let's first look at the structure definition of unmap command. The focus of the finger is parameter length, which indicates the total length of the unmap parameter data. The unmap parameter list is divided into 2 parts: unmap parameter list header and unmap block descriptor data. The unmap parameter list header consists of 3 fields: unmap data length, unmap block descriptor data length, and reserved. The unmap block descriptor consists of 2 fields: unmap logic block address and number of logical blocks. These 2 fields indicates the starting address and length of the block that the user wants to unmap. This is an overview of the 3 unmap structures, so that everyone can easily understand the structures of the unmap command. The 3 structures are very closely related, and we will focus on parameter list length and unmap block descriptor data length. Both fields indicates the length. Unmap block descriptor data length indicates the length of all subsequent unmap block descriptors. Parameter list length includes not only the length of all unmap block descriptors, but also the length of the unmap parameter list header. Let's see the VMware implementation. Before actually running the unmap command, the ESXi check unmap command function will be entered first. In this function, a heap of the corresponding size is requested according to the parameter list length, and all the unmap data is copied to the heap. After the unmap data is copied, the content of the data will be checked. But it forgets to check the relationship between parameter list length and the unmap block descriptor data length, and the number of unmap block descriptors is determined based on the unmap block descriptor data length. The user can set the special parameter length to carry a large number of unmap block descriptors, but only check the first unmap block descriptor. After completing the check, enter the actual use stage. According to the code in the finger, parameter list length is used as the boundary length, which allows the previously unchecked unmap block descriptor to be put into use. The unchecked logical block size is used as the size variable in the code shown in the finger, and obviously out of bound right. In fact, it is out of bound right that actually caused the crash, not the so-called out of bound read. Regarding the new attack service of VMKernel, I have summarized the following major impacts. It can modify the existing sandbox protection mechanism, and it can help us to elevate the current process privileges and help finish the virtual machine escaping. Okay, that's all our work about this presentation. Thank you for listening.